In this video, I'd like us to learn about yet another test for convergence of infinite series, the ratio test. So far we have seen the vanishing test and the comparison test. So this will be our third way of investigating whether a series, an infinite series, converges or diverges. The theorem that we will prove is this about this ratio test, which is sometimes referred to as D'Alembert's test. D'Alembert was a French mathematician. So the test itself does the following. We consider the infinite series that we are interested in, deciding whether it's convergent or divergent, and we assume that the following limit of ratios of successive terms in the sequence exists. So we take L to be this limit of the k plus first term divided by the kth term, both in absolute value, as k goes to infinity. So we assume that this limit exists, and then we have two cases. Then, if L is less than 1, notice that we are taking ratios of non-negative integers, so it is some non-negative number. If it is less than 1, then the series, our series converges absolutely. So it's not just converging, but absolutely converging. On the other hand, if this limit of ratios of successive terms in the sequence in absolute value is greater than 1, then the series is divergent. Then our series that we are interested in diverges. Okay, so let's prove this. Our proof, I'll start with the first case. If L is less than 1, is a number that is less than 1, then there is a number between L and 1. Okay, so a number Q such that L is less than Q, that is less than 1. Okay, so there's a number between L and 1, and what we can do now is, if L is the limit of these ratios, then there must come a point in this sequence when it gets closer to L, this limit of this sequence of ratios, than any previously fixed epsilon. And what we'll do is let epsilon be a positive number that is the difference between Q and L. So the distance between Q and L is our epsilon that we have chosen. Then there exists an index, let's call this capital K, such that our sequence of ratios of successive terms will be between L minus epsilon and L plus epsilon for all integers, for all indices that come after k. So this happens for all little k greater than capital K. Okay? But what is the right-hand side of this inequality? Well, L plus epsilon, by definition, is L plus Q minus L. This is how we have chosen our epsilon. But then, of course, what we have is L cancels, and we gain this number Q, which we picked to be between L and 1. Okay, and this happens for all terms in this sequence coming after the capital K term. Let's just translate this into the first few terms that come after capital K. So if this means that if little k is equal to capital K plus 1, what do we get? Well, we get the following inequality. We get that A capital K plus 2, that is the little k plus first term for this choice of little k, is going to be less than Q times A capital K plus 1. Okay? Because we have multiplied both sides by the absolute value of A little k, with this choice of little k being capital K plus 1. So this is what happens for little k being capital K plus 1. So let me just repeat here that what we have chosen to be is this special choice for little k. What's going to happen if we pick the next value for little k? We take capital K plus 2. Now, quite similarly, we'll get capital K plus 3 in the index, and it will be less than Q times the absolute value of A capital K plus 2. Okay, so it's just the same thing applied for capital K plus 2, but again, but now we can, for A capital K plus 2, we can apply the previous inequality to gain another Q times the absolute value of A capital K plus 1. So we have Q times Q, that is Q squared, times the absolute value of capital K plus 1. Okay, so we now see that the absolute value of the K plus second term is bounded above by Q times the K plus first term in absolute value, and the next one after that is also bounded above by Q squared times the K plus first term in absolute value, and this keeps happening. So in fact, what we'll see is that for all little k that we choose to be capital K plus L plus 1 plus L plus 1, what we will find is that A capital K plus, well, let me write it differently, capital K plus 1 plus L plus 1 plus L, what we can find is that we can always give this upper bound of Q times the previous term in absolute value. Okay, so the previous term is the capital K plus L term, and then we can keep doing this process of giving upper bounds until we reach the Q to the L minus first power. Okay, so if and with our term in absolute value, the K plus first term. Okay, so just check how these previous inequalities apply to if L is equal to, yeah, I should have the alpha power here. If L is equal to yes, I should have L here. Yes, so this is these inequalities we can give for the terms of our sequence that come after the capital K term. Okay, so if we go back and look at our original sequence, so now if we take a look at the absolute values of AK summed up, so namely we look at the K plus 1 plus Lth partial sum, of this infinite series will then be the following. We'll have to have the absolute value of AK summed up from K equals to 1 to capital K plus L, capital K plus 1 plus L, meaning that we have these absolute values added up from the first term till the capital K's term, and then what we'll have is we'll have the rest from the capital K plus first term to the capital K plus 1 plus Lth term. Why do we do that? Is that for these terms in the second sum we have these upper bounds. The first capital K term in absolute value is just capital K, is just a sum with capital K terms, it's just a finite number. So let me just write that this first one is the capital K partial sum, is just some finite number, so we don't have to worry about this. It's a finite number. And the rest, about the rest, we can make this upper bound to write, instead of these terms, to write that they are q to the power m times the absolute value of a capital K plus m plus 1 plus m, with m going from 0 to little l. Okay, let me try to write little l. Okay, so this is what we have applied here. This set of inequalities was applied here. Of course, I should say that it always goes back to the capital K plus first term, really. So this is the idea here. Okay, so each term has this upper bound of some power of q multiplied by the absolute value of a K plus 1, capital K plus 1. But then this, of course, is just a constant multiple of this expression, which is just the sum of powers of q. But of course, this will tend to 1 divided by 1 minus q, as L is taken to infinity. So this is, let me rewrite this is definitely less than or equal to this finite sum, that is the capital K's partial sum of our infinite series, plus a capital K plus 1 in absolute value divided by q, 1 minus q. And this is a finite number. So what we have seen, that our partial sums form a sequence that are nicely bounded above by this finite number, and they of course are an increasing sequence that are bounded above. So again, by either the comparison test or the monotone convergence theorem, we have a convergent sequence of partial sums of absolute values, meaning that this original sequence is absolutely convergent. And this concludes our proof. Well, the first part of our proof, if L is strictly greater than 1, we can basically try to use the same argument, but what we will notice is now we will have the opposite inequalities here, and what we'll have is a divergent geometric series that will, by the comparison test, will or the comparison of limits will force the sequence of partial sums to diverge. Okay, or even our original sequence to diverge. Okay, for an example, I would like us to look at the following. So I would like us to look at the example of the series 1 over k factorial, with k going from 0 to infinity. And I would like you to decide, using the ratio test, whether it's a convergent series or not. Pause the video, use the ratio test, and use the options below to indicate your answer. Okay, I hope you paused it and have looked at the limit of, well, in this case, ak plus 1 is 1 divided by k plus 1 factorial. And this has to be divided by the kth term, which is 1 over k factorial. We should take the absolute values of these numbers, but I mean, these are positive numbers anyway, so taking the absolute value doesn't change them. And this ratio is, of course, 1 plus 1 over k plus 1. If we simplify these factorials, only the k plus 1 factor will remain. And if we take the limit of this number, of this sequence, we get 0 for L. So this is L in the theorem. So what we have found that L is less than 1. So by the ratio test, this sum, this infinite series, is absolutely convergent. Okay, I hope you got it right, and I'll see you in the next one.